All right, so let's get back to our matrices and vectors. So who can quickly tell me what is this? So I have this a matrix A, 1, 3, minus 2, 4, and I have a vector 3, 2. Who can tell me the dimensions of those, that matrix and the vector?
2 by 2 and 2 by 1.
2 by 1. So what that means is that we have two rows here. The row 1 is in blue and the row 2 is in red. And the way we multiply matrices and vectors is that one thing that has to happen is that basically number of elements in the rows that I see here in the rows of matrix A has to match the number of elements in this vector, or the column, if you will. So when I say 2 by 2, 2 by 1, those, they're called inner dimensions. 2 and 2 have to be the same. Okay. If I had 2 by 2 and 3 by 1, I wouldn't be able to do this.
So it has to be number of rows equal number of rows.
Right. So that essentially you can go down and do the scalar product of this row vector and this column vector. So that's actually what, and if you can't do that, you can't do this multiplication. So let's write this down formally. Save. Not screen flow. Yeah. Okay. So let's write this down formally. So essentially, in order to be able to do matrix, in order to do matrix vector multiplication, I have to have inner, this is inner dimensions match. And what that means, if my A is m by n, so I have m rows and n columns, then my vector u is n by 1. These are my inner dimensions. They have to be the same. So I can multiply 2 by 3 and 3 by 1. Okay? 2 by 7 and 7 by 1. 7 by 11 and 11 by 1. Okay? So that way I will be able to do the scalar product of the row vector in corresponding row in matrix and the column vector that I have as u. Okay? So number of elements in each row of A has to be equal to number of elements in the vector.
Has to be equal?
Yes. Otherwise, I cannot do that scalar product. I have to have matching number of elements to go down.
I feel like we're going over this a lot more than we did last semester.
Just a feeling. I'm going to finish this in a week, and I did that in the last semester. Okay, so we can actually now extend this and not just do matrix vector multiplication. I can do matrix multiplication, basically by using the same rule. So I'm going to look at this second matrix that I'm multiplying with as a collection of vectors. And then I'm going to do a bunch of matrix vector multiplications. That's essentially what it's going to come down to. So let's give it a try. So we will still have to have, so basically instead of having a U that is n by 1, let's have another matrix n by L or n by K or something else, meaning that I have multiple columns in that matrix. So I can just proceed the same. So let's actually give it a shot with A. We're going to now change our A just for kicks. So let's have my A equal to 1, minus 2, and 3, and 3, 1, and 7. And I'm going to multiply it with B, which is going to be, I'm going to give it 2 columns. 1, and just for kicks, I'm going to put minus 0.5 and minus 0.5. So that we deal with a little more real numbers, though it's not terrible. So this is my B. So my matrix A is 2 by 3, right? I have 2 rows and 3 columns. So each row has 3 elements, right? Because I have 3 columns. So my matrix B has to be 3 by something. Okay. So B has indeed 3 rows and 2 columns. So 3 by 2. So this is this matching. So I can perform scalar product of the row vectors in A and column vectors in B, essentially. Now my result in this case will actually be basically what's left here is going to be 2 by 2. Okay, so I'm going to get a resulting matrix that is 2 by 2. Let's get the first element of that matrix. First element, and I'm going to give myself a space, some space for this 2 by 2 matrix. So I'm going to call this B, and let's call this C. So my C is A times B. Now, what is going to be the first element of C? Or rather, not first element, but element in the first row and first column. Okay?
1 times 1 minus 2 times negative.
Wait. So I'm going to do first row and first column. So element 1, 1 in C will be 1 row, first row in A, and first column in B. So basically I'm going to do a scalar product, okay, of this and that. Okay? So that is going to be, now you may proceed, 1 times 1. Now he's already done, so he doesn't want to. All right, 1 times 1, and then plus
negative 2 times negative 0.5.
which is 1, and then
Plus
3 minus, let's put a, I'm just going to do a quick change here to make my life easier, and just put a 2 here. Okay. So 1 plus 1 and minus, so that's going to be 2, and minus 1 is going to be 1. Yes? So let's now do element that is in the first row and second column. So first row and second column. Okay. So I'm going to do the same dot product between this row and that column. So that's going to be 1 times 1 plus 2, right? Minus 2 times minus 1, and minus 6, correct? So that is going to be 3 minus 6, which is minus 3. Okay? And then now we're going to keep going. So my element that I'm going to put here is in the second row and the first column. Okay. So that is going to be second row and first column of B. Okay, so I do the product. 3 times 1 minus 0.5 minus 7 times 0.5. Okay, I'm going to trust you on that one. Well, that's because I have it in my notes too. Ha ha ha. Okay. And then finally we have one more element to go, which in C is in the second row and second column. So I'm going to take second row of A and second column of B and do a matrix vector multiplication, or basically do a scalar product of the two. And let me choose a color. That one I will do in blue. So I'm going to do this and that. So it's gonna be 3 times 1 minus 1 is 2, and then minus 21. So it's minus 19. Okay. So we will refer to, so I basically verbalize what I'm going to now write down. We will refer to elements of any matrix really by first mentioning its row and then a column. So this here is a matrix and its elements are C11, C12, C21, and C22. Okay? So it's 2 dimensions, so I need 2 numbers to actually correctly locate any element. And similarly, so in A, I'm going to have A11, A12, A13, A21, A22, and A23. Right? So basically by referring to row and column. So if I were to formalize this a little bit, basically when I look at C21, so my C21 is dot product of second row of A and first row of first column of B. And the best part of this digital thing, it does have an eraser. So formally, if I was writing just referring to elements in the matrix A, it would be, if you remember that sum for dot product, right? It's essentially A21 times B11 plus A2, I'm still in the second row of B, so 2 times B21 plus A23 times B31. Okay? Because this is A21, number 3, A22, A23, yes? And this is B11, B21, B3. So we can kind of see the rule that this here is a matching number, if you will, because it refers to the location in row versus column. And if I was writing this as sums, I would write this as a sum. Let me use K from 1 to 3, A, 2, K, B, K, 1. So they're kind of parameterized by K. And the sum goes from 1 to 3. And the reason I want to write it this way is not because of this case where I only have 3 of them, but because I could have a 3,000. And starting next week, I want to start programming this. So I need to formalize how do I refer to all 3,000 of elements of something? Okay. And we're going to start formalizing that. Because that's the key where these machines are good. They're not going to do the thinking for you. They're going to do the computing for you if you're clear enough in telling them how to do it. So we have to establish the rules. And as I said, their machines are very, very much not accepting of small mistakes. So you have to be very organized and tell them what to do correctly. So overall, if I was thinking of even a general rule, okay, so I'm going to have so I'm going to have in general, so when I have a matrix product, so my C is A, B, and this is my M by N, and N by, let's say, L matrices. So if I want a rule, what every element of C looks like, I'm going to refer to that every element as Cij, not just 2, 1 anymore, but Cij in general. So my Cij, okay, is a sum. K now goes from not from 1 to 3, but from 1 to n, as many elements that I have in rows of A or columns of B. A I K B K J. So we can see that all of my elements of A are coming from row I, and that I can be any I, 1, 2, 3, as many as I have. And all of the elements of B come from column J. Right? So I have a dot product of I row and j column of ith row of A and jth column of B. Is that clear? So we're kind of step by step formalizing, and these steps are precisely what I need to start getting to the point that I can actually tell the computer how to do things in any case, not just like for 2 matrices that I type in. Computers are good at that too, but I want to program computers in a way that I can reuse the code. So if I want to write a code for matrix multiplication, I want that code to work for any matrix I give it. And that matrix could be 3 by 3, 3 by 7, 7,000 by 7,000, it doesn't matter, right? So these are the steps in formalizing that language so we can actually get to the point to have a rule that is translatable to code. Okay, so these are essentially quick things that I wanted to do as part of the practice, and now I'm actually going to go and open my presentation again and go over this in a little bit more formal way and a little more general matrices, so now that should it should be more understandable. So let's pick up where we left off. So we did the... Would it be helpful if I briefly review what orthogonal vectors and all that? Okay, so let's just go over the rules. So we introduced norms in general for vectors. So I introduced... Okay, swap this place. There we go. So in general, I can have any norm for a vector, but I'm just measuring how big that vector is, so I can actually compare it to others, and I can do that in different ways. And we define, we're going to use 3 major norms. One is 2 norm, which is, if I replace P by number 2 up there, norm 2 of x, is simply square of all of the absolute values of the elements of x, and then I take the square root. Norm 1, by the same rule, would be simply sum of those absolute values. Okay? And this is where I'm introducing my sigma. And then I have a max norm, which is, or infinity norm, which is simply maximum of all of the absolute values. Now, first place where I'm going to use that, so in general, any measure like this could be called a norm if it always is positive, so I don't want norms of things to be negative values. If I multiply my vector x by just a scalar, the norm of that new vector should simply be the absolute value of that scalar times them. And you can actually plug that in and prove it to yourself that is actually true for norm 2, for instance. And then there's also this triangle inequality that says that if I add two vectors, the norm of that addition is less than or equal to the individual sum of the individual norms. Now, first place where we want to use that is looking whether things are orthogonal. And I can define an angle between two vectors, which is, this is basically a dot product of two vectors. If I'm thinking of vectors and matrices, I actually have to kind of do a transpose. If two of them are column vectors, then it's transpose of the column vector u, which is a row vector, dot product times v, which is a column vector. And I have a norm 2 of u and norm 2 of v. We can also normalize vectors. If you're just interested in directions, then we're typically going to take so-called unit vectors, and it's basically just normalizing vector by its value, norm value. So if I just divide, this is now a scalar, so I just divide an entire vector with u. So I have a question for you. Are two vectors u, 1, minus 1, and 1, 1 orthogonal? Why?
Their product is 0.
So when I take cosine theta, using the previous rule, then the dot product of those two vectors, which is this u transpose v, is the dot product. That dot product is 1 times 1 times 1 plus minus 1 times 1, right? So that's 1 minus 1, that is 0. Cosine theta is equal to 0. Our cosine of 0 is 90 degrees, and that's orthogonal, right? Now, if I want to convert u to a unit vector, I have to divide it by norm of u. So if I look at the norm here, it's square root of 1 square plus minus 1 square, so it's square root of 2. Okay? So basically 1 over square root and minus over square root will be vector that has length 1, okay? But is in the same direction as my original vector. So those are my orthonormal vectors. All right. So now we moved on to matrices. And basically, if I wanted to do a more general rule than the couple of matrices that we played with that were like 2 by 2 or 2 by 3 or something like that, then I'm going to write a table like this, and I'm going to have dot, 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 dot for all the missing elements that I don't want to write down. So this is in general my M. I have M rows by N. I have N columns matrix A. And if I'm multiplying it, so here I chose to call this X with vector X that has N elements, then I have M by N and N by N1, so I can do that. And my vector B that I define, each element of B will be the corresponding row of A multiplying this vector X. And by saying multiplying, I'm thinking of a dot product. Okay? So my B1 will be first row of A, dot product X. So it's A11 times X1 plus A12 times X2. and all the way to a1xn times xn. My mth element of B will be nth row of A. It's going to be am1 times x1, am2 times x2, all the way to amn times xn. Okay. So then I say that my vector B is ax, and then actually I can actually see how in this transformation I mapped a vector with n elements to a vector with m elements. Okay? So this is your generalization of f of x is equal to 3x. Okay? In that f of x is equal to 3x, my result y, which is equal to 3x, was just a number that I went from one number to another number. Here I went from one vector to another vector, and those two have different dimensions. So that's what matrices allow us. And all of these are linear coefficients, so it's really a generalization of this, like, oh, number times x, coefficient times x, which is 3x. So this is just a more general way to kind of stretch and do linear transformations from one vector to another. Okay? And, well, I just verbalized this. I went ahead of my slide. I get carried away when I see matrix. I had to multiply it in matrix and vector. Okay. Now, if I had, as I said, we can actually see m by n. So I have these inner dimensions that have to match. Okay, because this is number of elements in every row, which is number of columns times number of elements in vector x. I can also see, when I go back, oops, here, I have x1 here repeating, x2 is repeating, xn is repeating. So if I think of this as a vector, this vector, B, is equal to x1, scalar x1 times this vector, right? Which is the first column of A, plus x2 times second column of A, plus all the way to xn times last column of A. Do you see that visually? This is the first, these numbers are the first column of A. These numbers, so if I put them in a vector, I can also see this process as, oh, well, my B is sort of a linear combination of columns of A with these coefficients. So my linear combination, if you remember, has to have those scalar coefficients. So there's just another way to see this. Okay. So you can either have these dot products of rows and a column, or you can see it as a linear combination with these coefficients of columns of A. Either way is correct. Okay? And we have, and sorry, I have MATLAB, so I went back to some old slides, not the one from the last semester, so I have to change all of the references to MATLAB to Python. I will do that, and I will change your slides. Okay, so again, if we have now multiple columns and not just vector x, and I put number of columns there, I still have to have the rule that number of elements in a row of A has to be the same as the number of elements in a single column of this matrix. I'm just going to repeat this procedure. So basically, I'm going to do a number of matrix vector multiplications, and I'm going to stack results into a matrix. That's another way to see it. So most generally, I'm going to have, so here I chose to call them M by R and R by N. Then my results, these inner dimensions kind of cancel out, and my result is M by N in the end. Okay? And this is, again, just to realize that each column of this resulting matrix is basically a matrix column. All right. So again, this is arriving at that rule that we will be able to translate into code. So if I have ith row of A and jth column of B, my Cij element, which is in ith row and jth column of C, is a dot product between that row vector and a column vector.
In the other ones we have I, comma 1, and then in the other one we have 1, comma j. Do we have to do that? Or?
Comma is
I mean, the letter A, it says I, comma 1, and then in the B it's 1, comma j. They're switched. Are we supposed
they're
to do
not
that?
switched
No, she's
because
not
if I
right.
look at the jth column, it's jth column that has to be the same.
So what she's saying basically is the ones are gonna cancel out.
Oh, okay.
So if I'm going so.
Twos are gonna cancel out. The R's are gonna cancel out.
If I have elements, this is a good point. If I have elements of ith row, all of them start by I, comma something. And that something changes from 1, 2, all the way to R,
Which is the number of columns.
which is number of columns. However, in B, I'm in a column. So it's something, comma, J, and J is a column. Okay? So where I is and where J is important. Aij is not necessarily Aj, except for very specific matrices. And those are called symmetric, because however you flip them, they look the same. Okay? And they're actually very important for a whole class of things that I shouldn't go into now, right? These symmetric matrices. But that's not the rule. That's not all matrices, right? So where you put I and where you put, who is first and who is second, it's important. Here I kind of like, in writing, I often don't write comma, right? You have to write it if it's A2, comma 32. You gotta have a comma because you don't know. When you put 232, who is 2, who is 32? Is it 23, 2, or is it 232, right? So comma is necessary sometimes. And that also means that when we write code, it's going to be necessary. Right? So you can't just write numbers altogether. All right. So one thing that is interesting about matrices is that AB is not the same as BA. So I know in regular multiplication of just like numbers, 3 times 2 is the same as 2 times 3. It's 6 both ways. That's called commutation. Doesn't work that way for matrices. I can actually see that if I had so here I have 3 by 3 matrix times 3 by 3. Result is 3 by 3. Fine. But let's say that I had 2 by 3 and 3 by 2. If I multiply a matrix, which we just did, 2 by 3, 3 by 2, my result is 2 by 2. That's what we did on paper. Well, I did it on computer, you did it on paper. Now, if I multiply it the other way, BA, it's gonna be 3 by 2 matrix times 2 by 3. What's the result? What's the dimension of the result? So in one case, I have a 2 by 2 matrix. In the another case, I have a 3 by 3. Obviously, they're not different. I don't even have to go and compute. Now, here and there, it might be the case, but you've gotten yourself a jackpot, or you multiply what's called an identity matrix. There's a matrix called identity matrix. Whoever I multiply with the identity matrix, nothing changes, just like multiplying with number 1. So there's that, you either picked a very special matrix, or you kind of score the jackpot by somehow finding that this is actually the case. Most often, it's not going to be even the same dimension if you have mismatching dimensions. And sometimes, you might not even be able to do the multiplication at all. So AB works, but BA you can't do. So that's something that is important to remember about matrices. So this is this special matrix I. So pick a matrix, and I'm going to just do 1, 2, 7, 1, and 3. And then, so that's your matrix A, and then take a 2 by 2 version of identity matrix, which is 1, 0, 0, 1, and do that multiplication by hand. Then I'm going to wait for you. So convince yourself that if I have identity matrix multiplying, so just do this multiplication, that nothing happens to the original matrix.
We only do A multiplied by B, right? Not B multiplied by A. That would be the same, actually.
Yeah, you can do either. In either case, you shouldn't change the original matrix. So from whichever side you multiply with identity matrix, it shouldn't matter. Okay? And again, if you flip the order, it doesn't matter. The inverse of the matrix is a matrix. So we know in general that if I have, so this identity matrix is generalization of number 1. So now if I think about number 2, I know that I can always multiply 2 times 1/2 and get 1. And 3 times 1/3 is equal to 1. 7 times 1/7 is equal to 1. So, you know, each of those cases is 1/2, 1/3, 1/7. I kind of like an inverse of my original number. For matrices, it's actually way more important to do. And we kind of do that all the time when we're solving equations, right? Well, for solving systems of equations, it's going to be important to define inverse of the matrix. And this inverse is another matrix such that A inverse is equal to A inverse A and is equal to identity matrix. So this is done only for square matrices. Otherwise, only one of these is true, and the other way I might not be able to do the multiplication. So only for square matrices. And it's very non-trivial to find out. With like 2, I immediately said 1/2, not a problem. Great question. I was about to answer it. So basically when I have, and I'm going to write that down so it's, because this is end of my slides, so I can just go back to the paper. So one thing that we're going to spend and why we actually need to formalize these matrices and know how to manipulate them and do things with them is so-called solving systems of equations. So I will be solving something called AX is equal to B. In other words, I will be, for given A and given B, looking for X that this is true. Now, I know if I had just a number, let's say that I'm going to say 3x is equals to 7, okay? And this 3 is a scalar, so I know that I can just multiply this with 1 times 3. 3x is equal to 1 times 7. So 1 times x is 7/3. I have a solution. And this is where this inverse of 3 came into play. Now, if I had an inverse of matrix A, maybe I can do this. And I didn't leave myself enough space. I'm going to do that in a moment. So if I multiply from the left, I just told you that it's very important in matrices that are multiplying from the left or from the right. It's not the same thing. So then if this is identity matrix, that's right here, then identity matrix times x is the same as x. Identity doesn't do anything to anybody. So my x is simply A inverse B. So if I had an inverse that I know, solving this would be as simple as doing this matrix vector multiplication. Problem is we don't have it. Problem is finding an inverse is as difficult as finding the solution of this system. And we will actually have to have numerical methods to do that. We will first actually, this is going to be, first we're going to do root finding, then we're going to switch to solving systems. It's very important. It is everywhere. Nearly all of you are doing or will do some differential equations. In reality, the differential equations that we cannot solve analytically, which is what you're doing in course for those that can be solved, for those that cannot be solved, and in petroleum engineering, that's most of them, okay? Especially when you go to a complicated geometry such as porous media and complex reservoirs. So the moment the geometry is complex, you can't do analytical solution of anything, even for simple equations. So then a lot of the numerical ways to deal with these differential equations will, after some work, come down to solving a system of linear equations. So in reality, sort of solving linear equations is the root of solving any other engineering problem in terms of numerical solutions that are a little more realistic than what we can do by hand. So that's why we're gonna do. Now your computer or any other matrix multiplication in itself is also everywhere. Think about this. So again, I told you that matrices represent these linear operations that transform a vector to a vector. So when I'm rotating, okay, I'm formalizing moving in this direction, which is a vector, to rotating and moving in this direction. So what I'm doing is moving this vector to this one. There is a matrix that describes that. So now imagine a movie or anything that you're simulating, somebody is doing computer animation, of rotating object. Every point on that object is described by a vector. That vector has to be multiplied by rotation. And what movie does, it really rotates it by 1 degree, and then another degree, and another degree, but then it gives you a fast movie and you think it's a smooth rotation of some sort, right?
That's why they
So
call
you
it
were
moving
assuming-
pictures.
Right, they're moving pictures, and it's really just a discretized number of pictures between this angle and this angle. You just need 90, okay? Not more than that. Your eyes are not good and your brain. Your eyes and your brain, okay? Are not good to notice the difference. So between this and that, what happened is your object got discretized. Let's say you discretize me into 1,000 little cubes, which is your pixels on the screen. 1,000, and then for every rotation by 1 degree, it's 1,000 matrix vector multiplications to rotate by 1 degree, and then replot, and then repeat 90 times. I have just told you the essence of computer programming. If you were doing that by hand, you'd never do that. You just would stop right there. Computer agrees. Okay? As long as you code up a program, define how to define a rotation, right? With a matrix, store that matrix, figure out discretize objects, step 1, into this 1,000 boxes, okay? And then just multiply, do this 1,000 times 90, 9,000 matrix vector multiplication. For you, a lot. For computer, it's a good day. Right? And you can actually easily write that down. With all of the skills that you have, you would be easily doing that. And that's computer animation. Go work in the movie industry if this petroleum engineering. So what I'm pointing out is that there are certain core tools, and we will be working on core tools. They're kind of there, and it's at the core of being a computational scientist and working with this. So there's a lot of things that you can apply in multiple ways, and a lot of those things are the ones that you actually work in your sophomore years, and then you kind of, those are the foundation, the basis, and then you specialize. So really your third and fourth year at this, you're going to become a petroleum engineer, but with that basis you could go. But think about that, there's like, you can go anywhere. Even if you finish petroleum engineering degree and you need to pivot and do something else later, you can pivot. You have this one. So all ultimately, it's actually at the bottom of things is suitable, right? This 9,000 matrix vector multiplication, right? So the devil is in the details, and we're gonna start with details next time. So I'm gonna, basically this ends the class for today. I am going to send you an email to install. Please come with a computer next time, and we're gonna start working on fundamentals of program. Homework will be posted today, and it's due on Friday. And it possibly has been posted while we're talking right now. So it's been approved, and it's routed to be posted.
Sorry,
Mhm.
I have a class right behind this one at the main building, so I may be late on Fridays. Is that alright?
So you're going to be late?
Maybe late on Fridays because of the class.
That's fine. Yeah, as long as I know. Yeah. Just send me just an email.
No?
Yeah.
Okay.
Just in case that there is a quiz or something,
Perfect.
then I know you're a little late. But it shouldn't be fine as long as you're here within the first 5 minutes. Yeah. Okay? Mm-hmm.
And for the homework is, I'm gonna